Hi, today we're going to look at special functions and their graphs. Most of the graphs that we deal with in this class will take on the shapes of what we refer to as the 8 parent functions. So let's take a look at what those 8 parent functions look like. The first one is the constant function, f of x equals c. Now c is just a number. Notice there's no variable. Now remember, f of x took the place of y, so whenever we had y equals a number, it just formed this nice horizontal line. The next one is the parent function to our linear function. This is what all of our y equals mx plus b graphs look like. The parent to that is f of x equals x, and it's just this nice slanted, perfectly straight line. Now the next two that we're going to talk about are polynomial functions. The first one is the quadratic function. We've talked about these before. The parent function is x squared, and this takes on this nice parabola. The next one is x cubed. Now x cubed takes on this shape where you take each x value and you cube it, and it takes on this S-shaped curve. Now, when you talk about polynomial functions, we could keep going x to the 4th, x to the 5th, x to the 6th, x to the 7th, and they take on similar characteristics. If they have even degrees, so if it's like x to the 2, 4, 6, or 8, the tail end behaviors here, they both go in the same direction. They either both point up, or if it was a frowny face, they would both point down. Where cubic functions, or odd functions, odd exponents like 3, 5, 7, 9, the tails go in the opposite direction. One goes off to positive infinity, and one goes off down to negative infinity. The next would be the square root function. This is where you take the square root of x. Remember, we can't take the square root of negative numbers, so we would have to start at 0 and positives. This takes on the shape of half of a parabola turned sideways. And the next one is the cube root function. And so this is where you take the cube root of a number. And remember, you can take odd roots of negative numbers, so you could take the cube root of -1 or the cube root of -8. Now it takes on a similar S-shaped curve as the cubic function, but it's turned sideways. The next is the absolute value function. This, remember, absolute value is the distance from 0, and distances are always positive, so this takes on a nice V shape. And the last one that we'll look at is the reciprocal function, or the rational function, 1 over x. This forms these little hooks where the function gets really big really fast in different directions, and they have these things horizontal and vertical asymptotes. Imaginary horizontal and vertical lines that the function gets close to but doesn't cross. Now let's talk about shifts in the graphs. We can take those parent functions and we can shift them. We can pick them up and move them up or down, or move them left and right. The thing to remember when you talk about shifts in the graph is that vertical is on the outside of the function, and it's exactly what you hope it is, and horizontal is inside the function, and it's actually the opposite of what you would hope it would be. So if c is a positive real number, then your vertical and horizontal shifts of the graph are represented as follows. Vertical shifts, remember, vertical is outside. If you're adding a number outside the function, you're going up that many units. If you're subtracting, then you go down. So this is outside the function. Up makes sense, it would go up, adding. Minus would go down, subtracting. Whereas your horizontal is inside the function. Now if you want to move to the right, then you subtract c. And I know what you're thinking. You would think that adding would go right, since to the right on the x-axis is positive, but it's the opposite. Horizontal inside the function is the opposite. So subtracting c, you actually go right, and adding c, you actually go left. So let's take a look at some examples. Let's look at this function, x minus 3 quantity squared plus 2. Let's determine the parent function and then discuss the shifts. Now this square on the outside here tells us that it's going to take on the parabola, so its parent is the quadratic function x squared. Now outside the function is vertical. Adding 2, it's exactly what you think, it goes up 2. Horizontal is inside the function, so inside the square you see we are subtracting 3. Subtracting 3, remember it's the opposite of what you think. Subtracting goes right. Now let's take a look at the cube root of x plus 5 quantity plus 6. Outside the function is vertical. We're adding 6 on the outside, so it's going to go up 6 units. And then underneath the radical is inside the function. So inside the cube root means we're adding 5, means we go left. So this takes the parent function, the cube root function, and it moves up 6 units and left 5 units. Now the last thing we're going to talk about are these things called piecewise functions. Piecewise functions are functions that are broken up into different pieces, and it's determined by a split in the x values. Now remember, functions pass the vertical line test, so when you figure out which piece the x value belongs to, it's only going to belong to one piece. It shouldn't belong to more than one piece. So when you evaluate your piecewise function, you figure out the x value that or the piece that your x value belongs to, and you plug the x value into that piece and that piece alone. So for example, we have this function, which is equal to 3x minus 5 for any x value bigger than 1, and x squared for any value less than or equal to 1. So let's say we wanted to plug in x equals negative 3, and we wanted to evaluate f at negative 3. We would have to figure out what's our x value, negative 3, and so once we know the x value, which piece does it fit in? Is negative 3 bigger than 1, or is negative 3 less than or equal to 1? Since it's less than or equal to 1, we'll plug it into this bottom piece. So f evaluated at negative 3, we would just take negative 3 squared, which gives us 9. Now what if we wanted to plug in x equals 1? Same thing. Figure out where 1 is. Is 1 bigger than 1, or is 1 less than or equal to 1? Since 1 is equal to 1, we'll plug it into this piece, and so we'll square it, and 1 squared is 1. Now if we wanted to plug in the x value 5 and evaluate f at 5, again, figure out where does 5 fit. 5 is bigger than 1, so we'll plug it into this piece. 3 times 5 minus 5 gives us 15 minus 5, or 10. Now when it comes to graphing piecewise functions, there's a little thing that you have to do. It's a little tricky. You need to plug in the x value of the split into both pieces. You're going to plug in 1 into the top piece and at the bottom, because that's where it's split. Now the top piece is only for x values bigger than 1, but it has to take on every single x value that's bigger than 1, and there's infinitely many. 1.1 is bigger than 1, 1.01, 1.001, 1.000000001. So we're going to start by plugging in 1, but since 1 isn't included, when we graph it, we'll give it an open circle. And then we'll plug in a bunch of different x values that are all bigger than 1. And then here we'll start by plugging in 1. Since this has the less than or equal to, it does include 1. So when we plug in 1, we'll graph that ordered pair with a closed circle, and then we'll pick only x values that are less than 1. So here I made a table of values. For the top piece, I plugged in 1, 2, and 3. Always start at the split. And when you plug in those respective values into their functions, you get their respective ordered pairs. But notice, remember, we said that you can't actually plug 1 into the top piece because it wasn't included. So we plug it in and we give it an open circle. Remember, open means does not include. And then we picked values bigger like 2 and 3. We'll do the same thing for the bottom piece starting at 1, but since the bottom piece did include 1, that'll get the closed circle. And then we picked x values that are less than 1, like 0, negative 1, and negative 2. And so then we can see these ordered pairs. Now, 3x minus 5, that's linear, so when we graph this piece, it should be a straight line. X squared is quadratic, so when we graph this piece, it should be part of a parabola. And when we graph it, you can see here's the top piece, starting in an open circle. Here's 3x minus 5 for only values bigger than 1. And then here's the part of the parabola for all values 1, including 1, and less than 1. And notice this is a function because it does pass the vertical line test. We'll discuss more about these parent functions and piecewise functions next time I see you.